Okay, so the single eigenvalue, single eigenvector case. Let me state again what the issue is. If lambdas are the same, the corresponding v's are the same, obviously, right? If you have a single lambda, you have a single v bar. Let's say that what happens. Then you have one component of the solution, you're missing the second one. How do we find the second independent solution? At this point, I want to remind you what we did actually when that happened in the second order linear ODE, right? So remember in that case, if we had two different roots of the characteristic equation, we had a very similar solution, right? Like we have in the system case. And if we had a single R, we actually proved that the second independent solution via variation of parameters needs to be t times e to the rt. So we actually proved that t times this solution will provide us the second independent solution. There is a slightly more involved proof that leads to the same type of method here for systems. I'm not going to go over the proof. I just want to emphasize why just multiplying by t the previous solution will not fix the problem. You have to take a slightly more general expression in front of that previous solution. A full linear function of t with vector coefficients. So that will be the fix here. But I want to illustrate why just times t, the previous one, just times t, will not do the job. And at this point, maybe we should write here as well that the fact that lambda and v bar are eigenvalue and the corresponding eigenvector, you can rewrite this stuff as a v bar equals lambda I v bar. You simply move lambda I v bar on the right hand side. So that's just another way of writing the fact that lambda and v bar are eigenvalues and vectors corresponding to each other, right? So v bar the eigenvector corresponding to lambda. So if I just try, for example, as a solution t times v bar e to the lambda t, is not going to work. Notice that if I plug it into the system, I have to use the product rule now. By the way, the product rule still holds if you deal with matrices here or vectors. So x prime would be, so on the left side, x prime will be v bar e to the lambda t, 1 times v bar e to the lambda t, so I'm doing here the product rule, plus v bar t, and then differentiate e to the lambda t, which gives me lambda e to the lambda t equals, and on the right hand side I plug in again, let's actually switch these guys, because you can actually put the scalar inside if you want to, so a v bar t to the lambda t. So you could actually interchange the scalar with the matrices. That's commutative, because in general the multiplication of matrices is not commutative, but the scalar can be switched from one position to another. So this is what happens if I plug in just the previous solution times t. It's not going to work. Notice I can cancel as before e to the lambda t, but a v bar is lambda v. Okay, so a v bar is lambda v, so therefore these cancel as well, and therefore this will lead to v equal the 0 vector, which we know it's not true. So we know that the eigenvector is not going to be 0, 0. That's how you found it. So if I simply plug in t times the previous solution, we're not going to obtain the second independent solution as we need, because it will lead to this v equals 0, which we know it's not true. So again, we're not going to move on with the actual proof, but the solution, the correct second independent solution that happens here is going to be in the form of a full linear function in t with constant coefficients, with constant vectors as coefficients here, and then e to the lambda t. So you're looking for a variation of parameters in which the coefficient of e to the lambda t, it's no longer just a constant vector like the eigenvector, but what we're going to call a generalized eigenvector. In fact, this extra vector u is the so-called generalized eigenvector. And I'll show you immediately how that comes to be computed. But I want to emphasize that in this form, again, V is the eigenvector that you just found in the previous step, right? Because you always start with finding the eigenvalues and vectors. And now you're looking for a solution in this slightly more general form, in which the coefficient of e to the lambda t is going to be this linear function in t with vector coefficients. These will be vectors with constants, and this is just the time variable t. So really the question is, how do we find this extra u, this extra vector that I introduced here, so that this combination provides me with the second independent solutions as I need. So let's repeat the process and plug this into the original system, and again carefully perform this product rule. So we differentiate the parentheses first when we plug it in here on the left side, so that's going to be v bar e to the lambda t. Then continue with the product rule, u bar plus vt, the derivative of e to the lambda t, which is lambda e to the lambda t. And the right hand side will be the matrix times x bar, so that's a u plus vt e to the lambda t. So again, the goal here is to provide me myself with a means to find this u bar. Let's distribute this. This is a scalar, so we can distribute these coefficients. So that's going to be lambda u plus lambda v bar t, and matrix multiplication is distributive, right? It's not commutative, but we can distribute a on this summation, a u bar plus a v bar t. And this, by the way, sometimes can be omitted, but this is also times the identity, actually. But we can drop this, because identity really plays like the role of 1, if you think about. And lambda v, remember, is equal to av, right? That's a property of the fact that v and a are v lambda are eigenvalues and vectors. So these two cancel, they are the same. And if we move this to the right hand side and pull out u, you're going to end up with a minus lambda identity matrix times u v. Sorry about that. I dropped the v. I forgot the v here. All right, so let's make room for it. So we dropped e to the lambda t. This is lambda u, lambda vt, and I forgot this guy. Right? So there's v plus lambda u, lambda vt equals that stuff. All good. So if I move this to the right hand side and pull out u bar, then you end up with this equation. So that's basically the key thing that gives you, and it will make much more sense, of course, when we go over an example, but this is the equation that gives you the so-called generalized eigenvector. Because if you look carefully, and that's the key thing, right? I mean, if you look carefully, the way to find u bar is by setting up the same system that gave you v bar. So let's rewind the whole process here. You find lambda, you find the eigenvector by setting this system. Then immediately after that, you set up the same type of system for a different vector, but now with not 0 on the right hand side, but with the eigenvector you just found on the right hand side. So the way you find u bar is really very similar to the way you find the original eigenvector. That's why it's called the generalized eigenvector. It's not truly an eigenvector, but in the way of finding it, the mechanics are extremely similar. So this may look a little bit kind of convoluted, but the mechanics of it will be very straightforward, as I'll show you right now. Okay, so without further ado, let's actually proceed with an actual example, and then we're gonna have another one on the next part. So let's see, suppose the matrix is minus 1 1 minus 4 3, and let's compute the eigenvalues, which will be only one of it. if you look carefully. So lambda squared minus the trace is 2, minus 1 plus 3, plus the determinant, which is minus 1, 3, minus negative 4 times 1. Very careful with the computation, because if you make a mistake here, of course, it'll ruin the problem. And then this simplifies to lambda squared minus 2 lambda plus 1, right? Because this is minus 3 plus 4. The determinant is 1 equals 0. So this factors into lambda minus 1 squared equals 0. And notice we have a single eigenvalue. We're not going to call it lambda 1 or lambda 2, right? I mean, it's the same. So just lambda equals 1. What about the eigenvector? So let's pay attention here. We pull out lambda from the main diagonal. So minus 1, 1, minus 4, 3 minus 1. V1, V2 equals 0, 0. And that becomes minus 2, 1, minus 4, 2. Notice the rows are dependent, which is reassuring, as they should. Like before, just pick any row you want and solve for the eigenvector. I'm going to choose the first one again. I'm going to choose V1 to be 1. And that gives me V2 equals 2. Okay, so the eigenvector, lambda again is 1, and the eigenvector corresponding to it is 1, 2. Okay, so here comes the new part, right? Once you find the eigenvector, set up precisely the same system that gave you the eigenvector in the first place. This is what we mean by this, right? So you're going to set up the same system, minus 2, 1, minus 4, 2, and now solve for another eigenvector. Let's call its entries u1 and u2. But instead of 0, 0, you're going to have 1, 2 on the right-hand side. So this is how you find the generalized eigenvector. And again, I want to emphasize the rows, including the right-hand side, are still dependent. If I multiply by 2, minus 2, 1, 1, I get the second row, minus 4, 2, 2. So how do you find the generalized eigenvector? In the same manner as you found the original eigenvector. You can pick any equation you want, like the first one, and extract a non-zero solution. It's going to be actually non-zero no matter what you plug in. So this time, a cool feature, if you want, I mean, an interesting feature if you want, you can plug in 0, and you should, because that gives you the easiest combination. You can plug any number you want, but now you're allowed to plug in 0 because the second one won't be 0 anyway. So as a vector, you're not going to end up with a 0, 0 generalized eigenvector here. So typically you will see people plug in either 0 for this one or for this one. I'm going to plug in 0 for u1, because then u2 will be 1. So one choice for u bar is 0, 1. But I want to point out again that you can, let's write it here because it's a little bit out of frame. So one choice for u bar is 0, 1. But any non-zero solution of this equation will do. For example, you could say, let's see, if I plug in 0 for u2, u1 will be minus 1/2. So you could say minus 1/2 and 0. That's not the nicest one, but it's also valid. Or you could plug in non-zero terms. For example, if I plug in 1 for u1, that means u2 will be 3. That's also fine. Okay, any non-zero vector will do. I'm going to pick 0, 1. That's the easiest one, the one that will have an entry equal to 0. So with that being said, and we rewrite in the next part the full formula, now the general solution will be again a combination of the first part, I mean the first combination, lambda v e to the lambda t, so v is 1, 2 e to the lambda t, which is et. And now the second combination, given by this u bar plus v bar t. So u bar was 0, 1. And then the eigenvector 1, 2 times t. And then again e to the t. So compare it with the formula sheet in your notes. You can make this a little bit more compact if you combine these parentheses into a single vector. So you could write it as c1, 1, 2 e to the t plus c2, not sure if I actually fit it, plus c2 equals, let's see, 0 plus 1 times t, that's t, and then 1 plus 2t. I get greedy sometimes with the space. Yeah, that's not good. Let me put it underneath. Underneath this one. So you can write x as c1, 1, 2 e to the t. That fits, yeah, plus c2 t, 1 plus 2t e to the t. Almost done. Yeah, we'll go over another example in the second part as well. Well, I mean, that's not important. What I'm saying here is that you could combine these parentheses into a single vector. But that's optional. I don't care if you leave it in that expanded form and like it's given in the formula sheet. So let's go over one more example with a single eigenvalue, and then we're going to finish up the discussion with the complex eigenvectors, which we're going to take our time with that as well. You probably should do that on a different day. I mean, I'm not expecting you to go over this in a single setting. So next part, another example of this, and then the complex case.